Hi everyone. Today I'd like to introduce our research paper called Competency Model of Shift-Left Architecture in Big Data. The authors are Vysotska, Iryna, Kyrychenko, Vadym, Demchuk, and Nadiia, Babkova. The purpose of this study is to analyze key challenges of implementing shift-left architecture, analyze its limits, trade-offs, barriers, provide a comprehensive approach to address key challenges, conduct an experiment, and of course evaluate the effectiveness of suggested solution. Big data has become a crucial part of huge enterprises, embraces different spheres such as IoT monitoring, personalization, fraud detection, science, and others. The traditional data architectures for batch and streaming bring some benefits in comparison to microservices approach. Without a doubt, enterprise success lies in transforming instant data to get immediate valuable knowledge. Let's consider traditional data architectures. The first generation is ETL, extract, transfer, plot, that is quite rare nowadays. Their processing engines take raw data from multiple sources such as on-premises databases, different third-party vendors, and other locations, transform data and load data to data warehouses for analytical purpose. Although this approach was good for its days, it has some drawbacks such as scalability issues, limited processing power, lack of tools to analyze spiced data. To address these challenges, ELT approach was emerged, that stands for extracting, loading, then transforming. It takes advantage of blob storages in cloud, also these technologies such as data lake and delta lake that are built on top of blob storages. The idea is that we first land data to the blob storage, to our data lake, then we do multiple transformations, multi-hop transformations. Although this ETL overcomes some challenges of ETL, it has notable drawbacks. Of course, still, we have delayed data insights because we have a chain of transformations. We have redundant transformation due to challenges of cross-team communications. Multiple team departments implement similar transformation against base first row tables. Of course, maintenance is quite complex and it's challenging to load data to operational system because it's not quite compatible. Confluent platform decided to overcome limits of ETL LT architectures. They introduced shift-left approach. The idea is that we move transformation to the left side, closer to the source, to create data products, so that we enrich aggregate data in the source. Then we build data products. These data products are consumed, these are data products, they are consumed by analytical systems and operational systems. Analytical for future processing, for creating reports, alerts, anything related to big data, and operational related to some transactional systems to create fast business results. So early data cleaning, aggregation, and enrichment guarantees that downstream systems consumes only relevant data. And we have backward compatibility between analytical and operational workflows. Let's look through related works. The first group of research paper consider weaknesses of multi-hop architecture, also called traditional data architectures. Of course, we have delayed updates because we have a longer data pipeline with multiple steps, with more tools involved. Of course, the more steps and tools we have, the more it takes time to refresh data product. Of course, we have extended time to market because of difficulty in cross-team communication. We have higher expenses on computation and storage, redundant work for implementing similar transformations in operational systems. And on top of that, we have to build some data reconciliation pipelines that will analyze any discrepancies, whatever we have in analytical workload and in operational workload. This is a huge disadvantage of this architecture. The next group examines the shift-left architecture and its benefits. So it has enhanced data processing efficiency, as we don't have expensive data transfer, data processing. Data itself has real-time nature. We get business insight faster. We have better data quality due to earlier issue detection. We have to pay more attention on data quality. I will discuss later why. And of course, it integrates analytical and operational workloads, hence faster innovation. The next research article is, although the previous one considered only benefits, this one also highlights it has some drawbacks. It's highly vulnerable to corrupted data, to bad data. Since we have to process data in the left closer to the source, we have to ensure we apply correct data transformation, correct quality validation rules. If we allow to process corrupted data further, it becomes a really challenging task to fix it, as this architecture, this shift architecture, is built on top of Kafka, where each record is immutable. We deal only with immutable data. It suggests, of course, this architecture suggests some steps to fix to prevent bad data through thorough design, testing, establishing a mechanism of like event-driven mechanism that will have to send an event to downstream services to fix some data. Well, while this is probably a good approach, these steps don't provide proactive measures to mitigate potential incidents and identify future performance issues. So, a stronger focus on predictive analytics and adaptive workload management could further enhance this architectural resilience. Since bad data is quite challenging for shift-left architecture, it requires some proactive steps. We would like to make some changes to this architecture and introduce additional modules that will enhance data quality and will identify potential risks, potential issues. So the idea was to take HLT implementation. What is HLT? It's holistic adaptive optimization technique. This technique is applied to a streaming data pipeline. But it's rather for ETL approaches. So we decided to extend this approach to shift-left architecture and reuse some optimization parameter tuning techniques using machine learning. The idea was the following. The sources, the things, the processing in itself produce a lot of metrics logs, so we have to collect them. We used data collection service from HLT implementation. We also introduced ML module for parameter tuning, for issue detection, for risk assessment. Although these parameter tuning exist in HLT implementation, it used different metrics. We extended these metrics. We have a control model that modifies key parameters, key configurations on the fly for this architecture, so that we have new metrics. ML model applies new changes these parameters, and this control model updates these parameters again until we have a better result of processing, CPU utilization, memory consumption, and other metrics mentioned later. Also, we suggested to use control center that will help developers to access and see the potential issues, risks for existing data pipelines. The next research paper analyzes what metrics can be used to analyze streaming systems. Of course, CPU utilization, memory, and network. So the most important is CPU. The better utilization, the more data we process. And then, of course, Kafka lag. This means that, for instance, in combination with CPU network and Kafka lag, we can understand, okay, is it a good processing? So if we have more Kafka lag, so we have more data in queue, then we consumes data slower than we receive data. So something needs to be changed. Let's go to the experiment. So we applied HLT approach, holistic adaptive optimization technique, to evaluate effectiveness of the current setup. So what we have here, we set up a system that has as a source Confluent Kafka, as a target also Confluent Kafka, where we have our data products. So here we have raw data. Here we must have data products. Of course, as a processing, we could say use Apache Flink, but we decided to use Kafka Streams because it's more familiar. We are more familiar with this technology. It's also applicable for shift-left architecture. And we consider it the mentioned parameters for performance tuning. From my perspective, the most important is compression type, max pool records, and of course the timestamp metrics. The dataset for testing had the following characteristics. It was 100 million records, a little bit more than 100, 24 gigabytes in size. Also, the environment was Kubernetes with 16 CPUs and 64 gigabytes of memory. That's not far for big data. Spark clusters have a much bigger setup. Let's go to results. So we conducted a couple experiments. So we repeated each group of experiments 3 times. The first one, we just used setup as is, just default values. The next one, we applied HLT that was changing parameters, and we fixed these parameters on the very last stage when it stopped changing them. As you can see here, the HLT suggested, the ML model suggested to reduce Kafka partitions. It was not changed on the fly. We applied it later. Also, the most important is that you can reduce some retention period problems. It's a best practice for Kafka not to keep for this huge period due to huge data volume. The interesting one, we increased linear MS. This is the max time we wait for collecting, for pulling data from source. Also, it was suggested to use some compression and other parameters. The more interesting other results. So as you can see, for HLT implementation, we have higher CPU consumption. While it can be interpreted as not a good result, I would say of course, we had a better data processor, more efficient. So what this experiment revealed during network issues, network limits. This IoT project chooses better parameters. We can see memory utilization also a little bit increased. That's not a problem. What is more important, network utilization per second, that's the same. This is because it applied data compression. But uh, we can see that Kafka lag was very small. We have a very huge difference of Kafka lag. It means that we was falling behind processing. We can receive data faster that we're consuming it. Here we can see it was just a pretty good result. It doesn't mean we had a big Kafka lag. It means that overall uh, this streaming has some time to trigger. And during this trigger, we collected some amount of data. But definitely per each trigger, we consumed more and more data. So this experiment showed that HRT approach can be very beneficial for shift-left architecture. On top of that, this competency model improved significantly data quality, and as you can see, it significantly reduced potential issue. In future, when we have huge, bigger workload, this pipeline would start processing it. It would require to um, stop it, to analyze some metrics, to spend some time, so that business will lose some, will have some financial losses. So this one, just better architecture. Of course, CPU utilization was higher, but data processing was much better. And if we have just lower workload, it's not a problem at all because we will have not that big CPU utilization in general. Well, that's pretty much it. Thank you for your attention.